Yeah, so multiple linear regression, I think some of you are touching it on your projects, but I think majority of you don't need it. But regardless, I think there's some useful stuff to mention. So it's I updated the slides, so there's some edits from last few. Yeah, I think page 58. Starting from there, I added a new topic here. So it's a multiple linear regression and how to do MCMC simulations by JAGs. So, well, multiple linear regression is the case that you're still learning, in this case, about a continuous univariate outcome. You have more than one predictors or more than one covariate. Sometimes you might hear the term like that, to help you determine what the relationships are, and then, of course, how to make inference about different coefficients. So just to bring us back to the problem, we started with this 2017 first quarter CE public available data. In fact, last time, or like when we started this unit, we only talk about the log expenditure and log income because we're using the simple linear regression, right? Like thinking about the outcome as the log expenditure and log income as the only predictor. And that's what we did so far in this unit about this regression. But in the same data set, there's this rural variable, which is binary. It's the rural-urban status of the consumer unit. Okay, if it's 0, it's urban. If it's 1, it's rural. Also, we have this race, which is a categorical. What we mean is that you can have more than 2 categories, and also, in particular, in this case, there is no particular order among these categories. So we call it unordered categorical variable. So the question is, how can we include additional information about the rural or urban status, as well as the race category, to predict consumer units log expenditure? And so this is what we typically mean by utilizing a multiple linear regression, that we're trying to use all predictors together to make a better prediction about the log expenditure, which is the outcome. Okay? We've seen how to do it with the log income. That's continuous, so we know how to interpret the slope as well as the intercept. But how about if you have a binary predictor, and how about you have a categorical predictor? How does those regression work? And then, of course, in the end, what if I want to include all of them? How can I interpret my results? So this is the last topic. All right, so when we're working with multiple linear regression, like pretty similarly to before the simple linear regression, we're still assuming this overall normal model. Okay? Sigma, the standard deviation of each observation, the normal model is still being shared. But we have this mu I, which is observation specific mean. Okay? In the past, we only have one predictor, so mu I is beta 0 plus beta 1 times xi. Okay? Now we're going to have multiple predictors. So generically, let's say we have r predictors. So now the mean of yi is a linear function of all predictors. So generically, we're writing mu I equals to beta 0, that's the intercept, and then like a beta r times xi r, depends on how many predictors you have. So all of the x's here, it's a vector of known predictors, and we know what they are. Okay? All of the betas, obviously, they're unknown, and we call them regression coefficients, and they are shared among observations as well. Okay, so that's how many parameters you have in this model. And then, of course, from the Bayesian point of view, if we're going to assume that they're unknown and random, we're going to give priors to them, and then see how the posterior summary will be. And those will be our estimation about those parameters. Okay. All right, so let's maybe just try out a little bit. So let's suppose right now, to start simple, all of the predictors are continuous, meaning that x1, x2, xi1, xi2, and xir, all of them continuous. What do you think the beta 0, the intercept, mean? And what does each of the coefficient mean? We talked about when you only have one predictor, continuous predictor, we talked about beta 0 and beta 1, right? That's the intercept and the slope. So what do you think now that if we have all, like many other predictors, all of them are continuous, what do you think those parameters, those coefficients mean? Take some time, check with your neighbor, and you're going to look at it together.
Because it can either be
what do you think? What does beta 0, the intercept, mean in this case?
When all of the predictors are 0, what's the expected y?
Yeah, so again, it's about mu, which is the expected value of y. So when all of the other ones are 0, which is all of the predictors are 0, like the log income, which is 0, or for the rural and urban cases when it takes 0, which I think is the urban, status. Well, I think for the race, the one that we worked with, anyway, never mind, sorry, we're talking about continuous. But anyway, so if you have a bunch of continuous predictors, beta 0 is the case where all of the continuous predictors taking value 0, what's the expected mean? What is the expected y, which is the mean, mu(i). So what about specific beta j? What do you think it means? Josh?
It's the expected increase in y
Mm-hmm.
for every increase in xj, given that all the parameters are kept constant.
Mm-hmm. Yeah, right, good. So I think many of you have this experience from before, so that's exactly how you should interpret it. So again, it's everything linked to mu(i), so that's the expected change that you're gonna have, okay? And when you're interpreting a particular beta j, you have to hold everything else constant, okay? So it's gonna be the expected change in the predictor j, like 1 unit increase in that, the expected change that you're gonna see in the outcome, okay, which is mu(i). So for continuous predictors, you can make the interpretation in a pretty straightforward manner. Like that's very similar to what we did before. However, the 3 predictors that I introduced to you earlier in the consumer expenditure survey example, not all of them are continuous. So a lot of income we know is continuous, and that's what we did before. Everything was overall straightforward. Binary, which is what rural variable is, and also race is categorical. It has 6 categories. So there's some subtlety here now that we're going to talk about when you're working with non-continuous predictors, how to define those coefficients and how to interpret those coefficients. So let's start with the binary predictor. Let's just say we're only using a binary predictor now. So the outcome is log expenditure. That's the one that we worked before. Rural, which is binary. So if it's urban, it's going to be 0. If it's rural, it's 1. So what I should mention is, yes, I mean, for a particular observation or like comparing 2 observations, it's like say everything else is the same, but you have one of them is from urban, the other one from rural, then that you will see the change between those 2. Okay? So you can consider rural as a continuous variable change by 1, but because it's the binary nature, we typically actually think about 2 groups in this case. The first is the urban group, and the second one is the rural group. Okay? So instead of thinking about the rural predictor as the continuous, we respect the fact that it's binary. So you have 2 categories here. And then when you have these 2 groups separate, what we're doing is we can directly work on the difference of the expected outcomes between the 2 groups. Okay? Say, for example, you have one observation in the urban group and another observation in the rural group. Everything else is the same. So the coefficient, which is beta 1 for this rural, so x rural I, the change in this xi, if you're going to have, say, a CU switching from one group to another, that beta 1 is capturing the difference. Okay. So maybe let me show you in a more, probably a better way to represent it in equation 45. So we can always write mu(i) equals to beta 0 plus beta 1 times xi. Here, xi is the only predictor which is binary. Okay? So imagine we know that when xi takes value 0, mu(i) just reduces to beta 0. Okay? So that is the expected outcome for the urban group because it equals to the mean, right? Whereas when you are in the rural group, your mean mu(i) becomes beta 0 plus beta 1, and that's the expected outcome. Okay? So from this setup, you can see how beta 1 is being interpreted. It is representing the change in the expected outcome UI from the urban group to the rural. Even though it's a 1 unit increase, as you can see from 0 to 1, but we try to put them into multiple groups. And you will see this as well for the categorical predictor. You just have many groups. And then you're trying to use one as the reference, and you use the other ones as the non-references. So what we're doing here is the reference is the urban group, and that reduces to beta 0. And then the rural group is beta 0 plus beta 1. And they're all just directly related to mu I. Okay, so that's how we interpret beta 1. And I'm going to pause here so I'll let you to think about, well, if I'm working with race, which is an unordered categorical variable, it has 6 categories. If we're also going to consider multiple groups, how many groups do you think there should be? And what are the groups? And of course, this classification of grouping is also putting emphasis on the difference of the expected outcome. Okay, so what I would do, or what I recommend you to try to write it out is, maybe can you write something similar to 45, but not for the binary predictor, for the categorical predictor that we're looking at, where you have 6 different categories. So think about how you're going to set up the model, and then we're going to look at it together. All right, so let me show one way to set this up. So again, it's a categorical variable. We have 6 different categories. So we probably want 6 different groups. We want to put all of them separate. And the thing is, for a categorical variable, we typically define one of them to be the reference group. So you can look at the difference. So each of the predictors or each of the coefficients going to be the difference of the group that you're working with compared to the reference group. So let me show you what I mean. So to start, I mean, just looking at the order of, it's unordered, but just because 1 through 6 is defined to be white, black, Native American, Asian, Pacific Islander, and the multi-race. So what we can do is maybe we'll put white as a reference group, which will reduce to beta 0, because that's when every other one's going to take 0. Okay, and then your beta 1 going to be the difference between the white group and the black group. Beta 2 will be the difference between the white group and the Native American group, etc., etc. Okay, so that's why in total you have beta 0, beta 1 through beta 5. And for each particular group, it's beta 0 plus some beta, because that's how we set up in this way. And you might notice that now we have many more predictors. So in fact, we only have 1, which is the race category. But in order to make the model interpretable, we are expanding, as you can see, them into what we call, maybe in other courses you've taken, what we call dummy variable. Okay, they are binary, because they can be either 1 or 0. If xi1 is 1, that means that this CU has a reference person as black. Okay, and similarly for this, all of the other ones. So my question for you really quick, 3 down here. What is the expected outcome mu I for CUs in the white group? What about for the Asian group? And what does beta 5 represent? Okay, so really quick, check with your neighbor, and then we're going to move on. Okay, so for CUs in the white group, it's going to be beta 0, right? For CUs in the Asian group, it's going to be beta 0 plus beta 3. And beta 5 is representing the difference between the white group and the multi-race. So what I recommend is, if you're going to work with a unordered categorical variable, you might just want to list all of them carefully at the beginning. So whenever you're like specifying a particular coefficient or specifying a particular prior, you know exactly where you're giving them to. And then of course later, when you're looking at your JAG summary of the posterior distribution summaries, you know what you're interpreting. All right, so all good to go. So if we're going to consider all predictors, just a little bit tedious here, you will have to write all of them out, especially. So here, beta 0 is going to be a general intercept, okay? And don't forget that we have this continuous income, okay? The log income, that's the first predictors that we consider, which is continuous. And then this is the binary predictor. And then, of course, when you have a categorical predictor, you're creating a bunch of dummy variables. All of the other non-reference groups all have to be added into this. So the final, here, just like before, when you're working with continuous data or predictor, you might want to do standardization. That's why I put a little star next to those, because they're being standardized. But if it's non-continuous, you can just leave them as they are. So the final multiple linear regression model can be written as, well, this is just in the normal case, we're still doing dependence, the sigma is still being shared, and that is something you need to give a prior to later on. So forget about that. A lot of times I think it's very easy just to focus on the mean, because that's all of the regression coefficients, but sigma is also being random. And the entire model will go from beta 0 to beta 7 times the multi-race category. Okay, so should be relatively straightforward from before. Right now we're just adding everything together. So just need to be a little bit careful when you're interpreting each of the betas here, because for the continuous you will have to, well, for any of the betas, I would say. I'm sorry, I should say for the continuous case you have to hold everything else constant, right? And then for the binary and the categorical case, you're thinking about the change, the expected change that you're going to have from the reference group to the group that you're working with. Lastly, before I show you the JAG script and all the details there, what do you think in this complete model here? What does the intercept beta 0 mean? What does the regression coefficient beta 1 mean? And what about the expected outcome, which is mu I, of a CU with Native American reference person living in a rural area with standardized block income 1? How can I express my mu I in that case? From equation 49, which is the key of the expectation linear function here. All right, so what do you think about beta 0? What does it mean? It is talking about specific situation of the mu I, right? For a specific group of people. What do you think beta 0 mean here? Anybody wants to give it a try? Might be a long sentence, but yes.
It's the expected log expenditure
Mhm.
for a white urban CU with log income 0.
Mhm. Yeah. So beta 0 is when every other x is taking value 0. Okay. So it's going to be log income to be 0, standardized log income, I should say. And then it's going to be not in a rural area, so it's an urban CU. And then it's going to be not of any of the non-reference group of the race category, so it's going to be the reference category, which is the white. Okay? So that's why Caroline was saying it's for beta 0 is for a white CU in an urban area whose standardized log income is 0. Great. What about beta 1? What do you think beta 1 means here? Anyone? Beta 1 is being applied to a continuous predictor. Okay, so for continuous predictor, we're usually saying that everything else stays the same. We're looking at a 1 unit increase in this continuous predictor. What's the expected change that you're going to see in the outcome, right? So in the context, you can say, even, yeah, say like for 2, yeah, you can say that for yeah, maybe you can say for 2 CUs in the same urban or like rural status, and then also a reference person race category if they're the same. Then beta 1 is capturing the expected change in the log expenditure. That if one of the CUs is having 1 times the log income dollar change from the other one. Okay. A little bit tedious in terms of interpretation, but the key is that you have to hold everything constant. And in this context, it's saying that you're looking at 2 households or 2 consumer units. They're both in the same urban status or in the rural status, and their reference person is in the same race category, but their difference is 1 unit difference in the log income, and then that will capture the expected change that you have between these 2. Okay. What about the last one? the expected outcome, which is the mu I, what do you think the mu I should be for CU of Native American reference person living in the rural area with standardized log income 1? I can just write whoever wants to volunteer. What will be the mu I star for this particular CU? Josh?
Beta 0 plus beta 1
Mm-hmm.
plus rural areas, so beta 2 as well, and beta 4.
Agreed? Okay, so let's see. So we want, so let me erase this one. Okay, so here we want a Native American reference person, so we should select this to be 1, right? Like xi raised n is 1. So n stands for Native American here. So beta 4 should be included. Living in a rural area, so beta 2 should be included as well because this value should take value 1, right? And then standardized log income, which is 1. So this xi star income is also 1. So beta 1 is being used as well. And then, of course, you have your intercept. Okay? So that's why this will be the final mu I star that you use. Okay? Yeah, for your, so again, all of the other ones about the binary and the categorical, they're binary. Okay, 0, 1, 0, 1. But this, the standardized log income can take multiple values. In this case, because we're talking about it equals to 1, so that's why beta 1 times 1. But if I'm saying that, what about standardized log income is 3, then it's going to be 3 beta 1. Okay. All right, I think, yeah, in the interest of time, I'm going to stop here. So what we're going to do, question?
Oh yeah, wait,
Yeah.
why was it beta 4 and not beta 3?
Oh yeah, so beta 3, okay, because right now we're considering all of the predictors together. So beta 3 is for race of black. So you see the little
Oh, I see.
over
I see.
there.
Yeah,
Yeah.
I
So
got you. Yeah.
so now, right? So the
Okay.
beta, like the index of them, they're different now
Gotcha.
from before because we're considering all of them. Okay. All right. So sounds good. So we're gonna end here. Happy Thanksgiving. We're gonna finish this, I think, most likely on Thursday after the break. Because on Tuesday we'll come back. We have a guest lecture about Bayesian two-sample testing. So there is a like a flow through part before. But then I will also invite a speaker to come here to talk to us about like his research. So most likely we're gonna like start a little bit later, like maybe 10 minutes later than usual, but I will send an email so we can like transfer the person from right here without any. Everything.